Well, today's lecture is 17.4, which is Green's theorem. There's actually two different Green's theorems, but they sort of get treated at the same time. I think before we launch into actually talking about Green's theorem, it'd be good to give you sort of a sense of the philosophy of what's going on. Remember the fundamental theorem of calculus? So let's just recall. That was going to be an F, and then I turned it into an R, so it looks weird. Anyway, recall the fundamental theorem. And you may recall that, in fact, there's multiple versions of it, but I think the simplest version of it is this one. If you do an integral from a to b of something that's the derivative of a function f, now that would be with respect to x. It was the x derivative, and so we're going to integrate with respect to x. You get something that basically depends on f, not on this derivative thing. And in fact, remember, it's the difference between f at b minus f at a. So the way to philosophically think about this is calculating a value over an interval. Over the entire interval, everything from a to b. You're calculating the height of this function, and you're getting, estimates of the area, and you're letting that Riemann sum estimate go towards the actual value, because you let the width of the Riemann sums go to 0. That whole business. Anyway, it's all happening over the entire interval, the interior as well as the endpoints. But this side, when you do f of b minus f of a, you're calculating only at the boundary of the interval. In this case, I should say boundaries, because there's two ends to an interval. So that's kind of strange, isn't it? That something that needs to be calculated by considering all the values across an interval can actually be computed by just looking at the endpoints. And of course, you're looking at a different function. Here it would be the derivative. Here it's, well, depends on how you emphasize it. You could call that f, and this would be capital F, the antiderivative, or call these f, and then that's df dx, like I've shown there. We just saw another version of this same kind of thing when we did the fundamental theorem of line integrals. Which said that if we were doing the line integral over some curve of something that looked like the gradient of a scalar potential, let's call it with respect to arc length. So if we were there's one more thing in there. That's the vector field. We're supposed to say T ds. Or that's a tangent vector for this curve. Of course, a nicer way to write it is the integral over c of grad phi dr. Anyway, what we found out was that in this case, where the thing you're integrating is actually essentially the derivative of something, this is the Calc III version of derivative of something, you can re-express it as phi at b minus phi at a, where I'm using the traditional letters for the beginning and ending of the curve. Right? The curve C might look something like this, and this would be A, and this would be B. So what really matters in calculating this integral, which happens all along the curve C, is find out how the scalar potential changes from one end of the interval to the other end, one end of the curve to the other end. You see how that's a similar thing? This happens on the curve. This happens only at the ends of the curve. Well, Green's theorem takes this up a notch so that we're looking at a higher dimensional place where we do the integrals and a higher dimensional boundary necessarily. So the analog when we go to 2D of this kind of thing because both of the examples I just gave you really are one-dimensional, to be honest. But in 2D, you could have a region in the plane. So this area, right? A region. But that area has a boundary. And the boundary, in this case, is the way I drew it with my marker as I went around. It started at one point, and at that point, it's a simple closed curve. So R is a region and C is a simple closed curve that forms its boundary. I guess the simplest way to say it is that C bounds R. So C is a simple closed curve that bounds R. Okay. So what do? We gotta sort of say what kind of things could we do across a region like that? And then what kinds of things can we do with the simple closed curve? And it turns out in both cases there are sort of multiple choices, but essentially you're going to equate a double integral over some region of, well, we'll say what in a minute, with a path integral or a line integral over the curve. And again, we'll say what in a second. This is what Green's theorem looks like. A double integral on the interior of a region, the interior part there of something, can be expressed as a line integral around the boundary. So this is on the interior, and this is on the boundary. Do you see why philosophically that's a lot like the fundamental theorem? In the case of an interval from A to B, right, A and B provide the boundary, and the interval is this junk in between. And we saw the integral of the stuff in between is equal to the antiderivative about, well, the change in the antiderivative at the endpoints. All right, so we got to get into more, what are the things that will double integrate, and what is the thing that will integrate? This is the setup you're going to have. You just talk about a vector field, F, and for convenience, we're going to need the names of the components of F. So F for the X component, G for the Y component. Really, both F and G are functions of two variables, because we're in 2D right now. Anyway, we're going to be defined on a region R. Just it could be defined on bigger than there. You need to make sure that the domain of F includes this region R, though. You don't want F to be undefined anywhere in the interior of R. And C will be the bounding curve for R. Great. So there are two different double integrals that show up in Green's theorem. They're both integrals over the region R. So this much is the same. One of them actually looks pretty simple. It looks like this. Take the x derivative of f and add it to the y derivative of g. So That is, the derivatives sort of match with the positions, f sub x, because f is in the x position, g sub y. This would be done with respect to area. Could be dx dy, could be dy dx, depending on how the region was shaped. You might even have to switch to polar or some other coordinate system for that integral. The other integral is weird because it has f and g switched and also a minus sign thrown in. So where this weird formula comes from, we'll have to wait until the next chapter to see. Actually, I think I'm going to give you a presage of it. But either g sub y minus f sub x. And again, integrate that with respect to area. And these two things, respectively, are equal to line integrals that we can do around C. This one is the line integral around C of f dot n ds. And this other one is the integral around C of f dot t ds. So the line integral that we started with is equal to this funky double integral where we need to calculate what g sub y minus f sub x is. The sort of second version of line integrals where we did the dot product of an outward normal with the function, with the vector field, that gives us the more straightforward thing in the double integrals setting. These are weird, and it's a little hard to memorize them, but that is something we're going to need to do. At least at first, we should just probably write it down on a crib sheet or something. But I think it's a good idea for us to take a moment and sort of understand where these two weird expressions come from. It is going to be, we're going to be looking at it a good bit more in, 17.5, but just crudely, I want to show you why they are the weird things that they are. And to do that, I've got to tell you about a thing that's called del. You've actually already met del. It's the weird triangle symbol that we put in front of a number when we want to, we put in front of a function when we want to get its gradient. Del is a vector that has operations in it. It has an operation taking the derivative with respect to x in the x coordinate, taking the derivative with respect to y in the y coordinate, and taking the derivative with respect to z in the z coordinate. Or if we were in 2D, you could have del, which would just be dx, partial with respect to x, comma, partial with respect to y. That is a strange entity before. You've never created a vector with anything but functions or numbers in it, but this is not a function or a number. It's the act of differentiating. This is an operator. And then del itself is an operator because it's built out of operators. Now possibly that's a bit of a new word for you, although it's been used in calculus before now. We talk about the differential operator. That's d by dx. This is just a more complicated differential operator. So it's not bad. It's not a bad idea for us to take a second and think about what do we mean by an operator. Personally, I think just by analogy. An operator is to functions the way functions are to numbers. That's the best way to grok it. So an operator is a thing that has a function as an input and produces a function as an output. that so much easier to say than it is to write? An operator is a thing that takes a function as an input and produces a function as an output. Del here can produce some pretty strange functions as outputs, depending on what you apply it to. Oops. Oh, okay. So the most straightforward thing to apply del to is an ordinary function. So if you take del and you multiply it times a function, that looks like this vector of things multiplied by a function. Do you know how when you have a vector times a scalar, you just distribute the scalar in? I'll write it in stages. This looks like partial x, comma, partial y. This is, I'm just writing down what del is, comma, partial z times a function. And let's just leave f without the of x, y, or z, or whatever it is after. Just look at it as if it were a scalar thing. If you had such a thing, you would just distribute the f in here. And so you would get a vector that had partial x times f. And sorry, it's all a little crowded here, but partial y times f, and partial z times f. And now we just have to face up to what does it mean to multiply an operation like taking the derivative with respect to x and a function. Multiplying means do the operation. That's what it means. So while it looks like it's multiplication, it's really, you put these two symbols next to each other and you're supposed to differentiate with respect to x, whatever f is. So I guess I'll crowd it still one more time into the corner of the board here. That's f sub x, that's f sub y, and that's f sub z. So we've got a function, a triple of derivatives of f. We've seen that before. That is indeed what grad f is. And when I write grad f like this, and I mean multiplication or scalar multiply, that's what you get, the gradient. So del times f is gradient. But you can, if you think of del as a vector, I know this is getting a little weird, but if you think of del as a vector, you can do other stuff with it. In particular, you can do the dot product of del with something and the cross product of del with something. So let's look at what some of those things turn out to be. If I have the del operator dotted with a vector field, what does that give us? All right, so yeah, if we do grad dot f, where f is a vector field, well, what does that look like? It's going to be this del operator, partial x, partial y, partial z, dotted with the vector field, which is going to have its component functions, f, g, and say h. And when you do a dot product, you put matching things together and then you add up. So you multiply the matching things and then you add. So you get partial x times f plus partial y times g plus partial z times h. And that's really, that's really f sub x plus g sub y plus h sub z in the other notation. And you might notice that the thing that we were double integrating over the region in one of the versions of Green's theorem was this. So when you're in 2D, that would be the equivalent of del dot f. This is the 3D version of it. But if you're in 2D, it just means you don't have that third component. You have either that or the h. So you just get fx plus gy. Lastly, we need to think about what do you get if you do the vector operation of cross products in here instead of dot products. So what does del crossed with a vector field f look like? I can make that change in two places to sort it out, but of course this is all wrong now. So what is the cross product going to look like? Okay, this is a pain in the butt. Well, you have to do the determinant, right? I'm going to introduce a little shorthand that people use because it's just a pain to keep writing partial x and partial y. So we'll write partial x like that to mean the x derivative, partial y for the y derivative, and partial z for the z derivative. Actually, that's a non-standard thing, but a lot of people I know use that kind of a shorthand for it. So, and then we'll have f, g, h here. All right, so remember how to do cross products. So the I component will be multiply these two and subtract those two. Let's just jump to the chase then. The thing that goes in the I component is the y derivative of h minus the z derivative of g. That is h sub y minus g sub z. The j component is going to be partial z of f, which is f sub z, minus partial x of h. And the z component is going to be, well, it'll be g sub x minus f sub y. I don't have room there, so g sub x minus, wait a minute, what was it again? Yeah, the x derivative of g minus the y derivative of f. And I don't know if you'll recognize it here, but if we're in the situation where the flow is really two-dimensional, or it's a two-dimensional thing, it turns out this one and this one become 0. And the only thing that survives is that, g sub x minus f sub y, the z component of this calculation, del cross f. So that is actually where the two things that we were integrating in Green's theorem come from. One is one of the components of this calculation, this cross product calculation. This has actually got a name. This is called the curl of f, and capital F. And the other one, which is no longer on the board, but it was f sub x plus g sub y. That one is known as the divergence. Of f again. So curl and divergence are big topics. These are just the two-dimensional versions of them, but they're understandable and make sense in 3D. And really, they're in a sense the components of the total form of differentiating a vector field. But that's a little beyond the scope of what we're doing in this course. So let me do a quick recap of Green's theorem. One thing is a double integral over the region of the curl, which is g sub x minus f sub y with respect to area, is the same thing as a path integral around the boundary of the region of, well, the vector field dotted with the tangent vector of that path done with respect to arc length. There's so many different ways we have of writing down what that means, but that's the variant I want to look at for in general. This part here, g sub x minus f sub y, is something that you can sort of imagine happening at every single point in the region. You know, I'm just drawing a few of them, but there's all kind. You know, there's a continuum of points throughout that region. At each one of them, you get a number g sub x minus f sub y, and it tells you locally what's happening to the flow. What people usually do is imagine putting a paddle wheel into the you know, imagine the flow as a liquid, and you put a paddle wheel in. I don't know if you guys have seen a paddle wheel before. I'm not sure if I can draw one in perspective, but they used to be the way they made ships move. They would have a big wheel, often on the back of the boat, sometimes on the side of the boat, and it would have horizontal boards sticking out of it, right? And then a steam engine would make this thing turn. So you'd have all these horizontal boards, and if the bottom edge of it was sticking in the water, as it turned, it pushed you along. Well, that's the image you have. But take that paddle wheel and lay it on its side and plunk it down into the flow. And see what it does. Does it stay centered? Does it start turning one way or the other? You'll find that, for instance, if the flow is large on one side of this and small on the other side of it, yeah, well, even though the flow seems like it's curving that way, what's going to happen, because it's going faster on this side than it is on that side, is the wheel is going to begin to rotate that way. So there's this sort of way to think about measuring at every point in the region how much it's rotating, how much the flow is spinning things. I'm sorry, I'm supposed to be making you think there's a flow in here. There's vectors all over the place in this thing that are moving around. Now, at each point, there are no vectors that curve like that. You got to keep your vectors straight. But anyway, at each point in here, if you drop in a paddle wheel, maybe it looks better if I do like that. This guy is going to spin like mad, isn't it? Because I've got vectors above that are going that way, and vectors below that are going that way. So there's a lot of spinniness in the flow right there. What this is telling us is that if we integrate over the full region, the amount to which these paddle wheels get rotated, it's the same thing to just go around the boundary of the region and look at how all the arrows line up with the tangent vector. You can see, actually, I've got a flow that goes around the perimeter of this thing, just because of the way I sketched it. Well, that would contribute a large number to this line integral. So yeah, that's the one version of Green's theorem. Could this happen in reality? Suppose you had a swimming pool with that shape. Could it naturally arise with this kind of a flow in it? These vectors like that, showing the way the water was moving? No, it really couldn't. If it did, I would put a paddle wheel in it and hook that paddle wheel up to a generator, and my house would have free power, right? This is only happening like this if energy is being supplied to this thing from somewhere. So this so-called, let's get the right name for it. This is the curl circulation form of Green's theorem. Anyway, the curl circulation form has to do with vector fields that do not obey the conservation of energy idea. If you had a flow like this, it would mean that you could extract energy from that flow, and that's not normal. Or another way to put it is, the only way it got established to be flowing like this is if somebody put in some kind of motors to make it go. Little, outboard motors stuck in around the perimeter of this thing to make the water flow around in that sort of position, in that sort of form. It'd be a little odd. So when you think about the curl circulation form, you should think about conservation of energy. Normally, if something is showing this kind of behavior, it means some energy was applied. And if it just does this naturally, you've got a system that violates the idea of conservation of energy. There's similar way to think about the other form of Green's theorem, which I guess I'll do lastly. So the other form of Green's theorem is a double integral over the region of the thing that just looks, well, this is del dot the vector field, f sub x plus g sub y dA. And that's the one that looks like the integral of the field dotted with a normal vector. By convention, it's always an outward facing normal vector with respect to arc length. Now the picture for this is, again, you've got some region. And remember how we think of this. If the vector field lines up with the normal vector, that contributes a positive amount to the path integral, the line integral. If the field is in the opposite direction from the normal vector, then, well, you've got a negative amount. So if you go all the way around the perimeter and the amount of flow across the perimeter is the same as the amount of flow out of this region, you get a zero integral for that. And that's where conservation of matter actually runs in. If you think about what it means for matter to be conserved, you must have, in any physical region, you must have the same amount of flow into it as out of it. What if you didn't? What if you had a flow that looked like this? The vectors are all leaving the region. Because I can certainly make a vector field that does this. I can even, I'll try to draw even some more of them in here. We're getting them littler as we come towards the center. I'm running out of energy, but there's definitely flow across the boundary everywhere. This line integral is large, and in that case, if matter is conserved, you have to be asking yourself, where is this matter coming from? That's all this flow that's going across the boundary, lining up with our normal vectors. Right? We'll have a little n there and an f here. Those dot together and give you some positive quantity. Then you integrate around the boundary and you add up a whole bunch of positive things. You get a lot of stuff there. So clearly matter is not being conserved, or else what really is the case is matter is conserved. We're just not aware really of where it's coming from. There must be like a pipe coming in from above that's delivering water to this area so that it can begin flowing outward the way it's shown here. In any case, there's a local way to, at any point, think about how is the stuff spreading out. You can imagine putting a little loop, casting a little loop of elastic material into the water. Would it expand out and begin stretching? Is it going to, a few minutes later, look like that? Maybe a loop wouldn't be the best idea. Maybe you should just scatter some junk, scatter something that floats. I don't know, peanuts, those packing peanuts. Scatter them into the water and then watch how they separate. Do they separate, or do they stay clumped together and move off to the side? If they're separating, that's measured by this. F sub x plus g sub y. This is called the divergence of the field. It's the tendency everywhere in there for things to kind of spread apart. And when you figure out across the whole region how much stuff is spreading apart, well, you can tally that up at the boundary. That's kind of the point. That's our integral around the boundary of the flux across the surface is actually the same thing as all the individual amounts of spreading out that happens across the interior of the boundary. So this variant of Green's theorem, last thing to say about it, this is called the divergence flux form. So that's divergence. This integral is called a flux integral because it's got the n rather than the t in it. Anyway, if the divergence flux form, if this sort of picture is non-zero, it means matter is either being created or destroyed or introduced from the outside or removed from the outside. somehow the system is not closed when it comes to the existence of the full set of material. Okay, so probably the last thing we ought to do is a quick example. So here's a really nice simple example to get started on. The vector field is got a 0 in the x component, and its y component is equal to its x position. So if you want to think about what that field looks like, when you're at the origin, it's 0, so you don't have a 0 vector there. When you're over at 0, 1, it's a vector that goes 1. Yeah, that's 1, 0, the point, 1, 0. But the vector is 0, 1. When you're on the x-axis at -1, comma 0, that was a poor choice of where to write the label because it's going to be, the vector is going to be going down from there. It's going to be like this. Actually, anywhere on the y-axis, your x-coordinate is 0, so you get a whole bunch of 0 vectors here. And anywhere where the x-coordinate is 1, you'll have a flow of a bunch of vectors that are copies of that one. That is, the field looks the same on vertical lines. And if you go a little farther out, it just gets longer. I have to draw them overlapping because I didn't scale things the way I probably should have. Okay. Now, if I want to draw things, if I want to include my unit disk, that's this guy. A little lumpy on that side, whatever. So we're talking about integrating over either this region or around this boundary curve for the region. And I'm going to do the circulation version. That is the curl/circulation version. So it should be the case that the double integral of, let's just write it as g sub y, always doing that, g sub x minus f sub y dA should be equal to the integral around the curve, which in this case is going to be, the circle, cos t sine t, of this, this is the curl, so I want to get the circulation, which is going to be f dot t ds. Great, so what is g sub x and what is f sub y? G is this second function, right? I should probably point them out to you. The first one is f, the second one is g. So g sub x is x differentiated with respect to x, so that's 1. And then minus f sub y, well, f is 0, so when we differentiate it with respect to whatever, it's 0. So this guy is a 1. What we've got is the double integral over our region of 1 times dA, or just dA. That should be the area of the region. Do we know what the area of the region is? Because, if you integrate differential area, you ought to get area. Yeah, this is a circle of radius 1, pi r squared gives us pi. This is pi. Just as a check. Let's see what f dot t ds looks like. Remember that you can re-express that as integral of f dr. This is the thing where the tangent vector ends up being divided by the speed. You take r prime and you divide it by the speed, and the ds is related to dr by, ds is related to dt by, the same factor. And remember they cancel? We did that in the last worksheet. So another way to write that is, integral of f times r prime dt. R prime t dt. And that's the one we're probably going to want to use for calculation purposes. That integral is also done over the circle. Actually, since we've changed this to an integral where t is the variable, we can think about the t limits for that. We would go from 0 counterclockwise around the circle and back to that same location, but that's 0 to 2 pi. Well, let's see if we can do it. What happens to f while we're on this circle? The x-coordinate is cos t when you're on this circle. So f is the vector 0, comma, cos t. And this one is 0 to 2 pi, 0, comma, cos t. That's what f is. And r prime, that is minus sine t, comma, cos t. And then dt. This dot product just gets us cos squared t. Right? 0 from that, cos squared t from that. I guess I need to make more board space. Right, so do you remember how to do that? Cos squared t, that's one of these trigonometric integrals. There's a half angle formula that you can use that cos squared t is the same thing as 1 plus cos of 2t over 2. Oops. I'm hoping I've remembered that right. I just popped open the book. There's always a question in my mind whether it's a plus or a minus here. But you can always go into the book and find it, the half angle formula right inside the front cover. 1 plus cos 2 theta over 2. I did it right. Ooh. So when you actually do the integral here, you end up with, let's see, t over 2 plus plus sine of 2t over 4. And that gets evaluated from 0 to 2 pi. Right, and this term involving the sine, that's going to be 0 at both ends, right? At upper limit of 2t, you have sine of 4 pi, which is 0, and the sine of 0 is also 0. So that term just doesn't matter. So we just have 2 over t evaluated between 2 pi and 0. Well, okay, that's pi. So we previously saw that the double integral gave us pi, and the line integral around the perimeter also gives us pi. Kind of checking, verifying that indeed Green's theorem holds in this case, but it holds in general. All right, that's it for today.